Hello everybody. So in this video we're going to continue the discussion on the dimensionless parameters and the advantage of using dimensionless parameters, and we are going to extend this on dimensionless equations. So we are going to discuss this in a very simple example. I'm not going to do this on fluid mechanics example, just to make things simple and to get the point easily. So this example that we are going to discuss here is about a very simple physics problem. It's a high school physics. It's about throwing an object upward, and to describe this location and velocity of this object as a function of time. So the equation that describes it is the change of the velocity with time is negative g, and the change of velocity with time is the or the derivative of velocity with respect to time is the second derivative of the distance with respect to time. We know the initial height or initial velocity is u node, the initial height is z node. So if we want to get the height as a function of time, we will integrate the equation twice, and with the integration we'll get to constants. We use the initial condition, time equals 0, u equals u node, time equals 0, z equals z node, and finally you will get this equation. And this is what I want to get from this slide, that this is the relation that we have between the height at any time as a function of the initial height, the initial velocity, the time, and the g, which is the acceleration due to gravity. And the equation that we see here is a dimensional equation because it has units of or dimensions of length. That's why this is a dimensional, not dimensionless equation. So this exact same equation can be rewritten in a non-dimensional form. So it's just another way of expressing the same equation. I'm not doing anything different. And this equation can be turned into a dimensionless equation by dividing by z node. So if we divide by z node, the equation is z over z node equals 1 plus u node t minus gt square over 2z. So all these terms here are now dimensionless, and we can define dimensionless parameters now. So we can define z over z node to be z star. It's a dimensionless distance, and it gives us an idea of how what is the distance traveled by the object relative to the original distance. So this gives us some insight of the relative distance of the travel distance to the original distance. U node t over z node is a dimensionless time. Froude number is u node over square root z node, gz node. This is called Froude number after the scientist who developed this dimensionless number, and it's a ratio between the inertial forces to the gravitational forces. So if again, this is something we mentioned last time about the importance of the dimensionless numbers, that they give us or dimensionless parameters, they give us some information about the system. It's like Froude number here. If you know that there is a system that has high Froude number, it means that it has more inertia or high inertia relative to the gravitational forces. So you expect this body to travel upward for bigger distance compared to the systems with low Froude number. So now we can write the equation in terms of these dimensionless parameters, and it's going to be z star equals 1 plus t star minus 1 over 2 Froude square times t star. Okay, so this is the equation that we have right now. So the comparing this equation to this equation, there are some advantages that we have when we express this equation in this form relative to the dimensional form. The advantages, the first and one of the very important advantages of this expression in dimensionless form is that it can show or we can understand using this equation the similarities in case of different scales. And to understand this, let's consider these two systems that we have here. One of them is a body is traveling, it traveled upward and then it's moving downward now. So that Z is 5 meters compared to Z node of 10 meters, while this system is Z is 250 meters compared to Z node of 500 meters. So this system to the right is 50 times the size of the system to the left. Okay, so it's much bigger, and you can imagine how is it going to be, because this is around three stories of a building. So this is something, a height that is kind of achievable. We can do something like this, but this is 500 meters. It's a lot. It's too much of a distance. So making an experiment with this scale is possible, while with this scale it's going to be very difficult to do. So if you compare these two systems and calculate Z node for these two systems, it's going to be the same, exactly the same. It's Z over Z node, it's 5 over 10 is 250 over 500. So the equation now can be, with the substitution of these dimensionless numbers, you get the output of the system regardless the scale of it. So it's a very important thing that it rules out the effect of the scale of the system. Why is this important, or why is this useful? It's useful because now we can use, or this expression of the equation that rules out the size of the system enabled us to use charts like this. And this is a very common thing in engineering applications, to have charts that relates some parameters. So this relates T star to Z star and Froude number square. So from this you can see that these are the three parameters in the equation, and we already have some lines. So if you know that, let's say, Froude number is 1 and T star is 1.5, so you know that Z star is 1.4. This Z star is the ratio of the height to the original height, and it doesn't take into account the actual value of the original height. It's giving the ratio. So it works for a system that is 10 meters big, 20 meters big, 50, 100, 1,000 meters big, it doesn't matter. Okay, so this is a universal chart that can be used to express any system. While if you think of a chart like this, if you want to make a chart like this for the dimensional equation, it is going to be a very huge chart, because you need to have X scale from 0 to I don't know, 30 minutes, 40 minutes. So it's going to be much bigger than this. For the height you have, it has to be from few centimeters up to hundreds of meters. So it's going to be a huge scale. While in this case you have a very limited scale for Z star, for T star, and it works for all systems. So this is, it gives us a good way of, using the dimensionless equations, it gives us a good way to rule out the effect of the scale of the system, or the size of the system, and at the same time it makes it easy for us to use such charts. Okay. So this is a very important thing, and inshallah in next chapter we will see a chart that is built in the same way, so we can use it to get some outputs about the fluid mechanics systems. One other advantage, which is a very good advantage about this, is that in the original equation we had the parameters that were involved in the system were 5. So the variable was Z, and the parameters is Z node, U node, G, and T. So we have a parameter function of 4 other parameters, while in the dimensionless equation we have one parameter, one variable function of 2 parameters, which is T star and Froude number. Okay, so the point here is that we were able to reduce the number of variables that we or parameters that affect the variable of interest to us. And now this will raise a very important question: why is this important, and why would we care about reducing the number of variables? To understand this, let's consider a general case. The case that we discussed here was an equation that we were able to derive from a basic equation. And with this derivation, we're able to reach the final form of the equation. However, there are cases where we get the relations experimentally. And this is a very, very common case. It's, for a lot of cases, we don't have the ability to do the derivations of the equations to reach the final form of the equations that relates the parameters to the variable that we are interested in. So let's say we have a parameter x that is dependent on 5 different parameters. So x is function of a, b, c, d, and e. And we are interested in doing some experiments to study the effect of the 5 parameters on x. So we can design our systems accordingly, and we can make the or have a good understanding of this effect and act accordingly. So let's say these are the 5 parameters that we have, and we want to study the effect of each one of them. So the simple thing that we all or will jump into our minds is that we will fix 4 of them and change only one. And based on this, we can understand the effect of each parameter. So we will start with, let's say, a. We will keep all the parameters constant. So we'll keep b, c, d, and e constant, and we will only change a. We will change a 10 times and then get the relation between x and a, and then repeat this for the other parameters. So we will have 5 tables like this. For each table, we have constant. 4 parameters are constant. Here, b, c, d, and d are constant, and we vary a. Here, a, c, d, and d are constant. We vary b, and so on. So theoretically speaking, we will be able, by this approach, to get the relation or to understand the effect of each one of these parameters on x. However, there are some questions that will jump into our mind when you think of this more deeply. The first is, what are the constant values that we will pick for the 4 parameters? And here we decided that the parameters would be b, c, d, and e. So will we pick them as 1, 1, 1, or 1, 2, 1, 2, 3, 4, 100, 200, 300, 400? What are the values of a, b, c, or b, c, d, and e that we pick? And the values that we pick here, are they going to affect the results we get? Okay, we expect it to affect, of course. So if we choose another set of constants here, and here let's say this is b1, c1, d1, and e1, and we took the first values. If we do the same experiment with another values for b, c, d, and e, let's say b, a2, b2, c2, and e2, then these numbers will vary. Okay, it's not going to give the same output. So this is the question here. So to make it more accurate and to take this into account, we can do the same procedure, but we will do this in more iterations or more cycles, meaning that I will keep b, c, d, and e constant, and then change a 10 times and do the experiments, and then choose another set of values for b, c, d, and e, and then change a 10 times. Yani let's say we are going to do, we will make 10 of this table. We will have a varying from 1 to 10, and the values of b, c, d, and e is b1, c1, d1, and e1. And then we will make another table like this, but these constants are b2, c2, d2, and e2. And then another table like this, but this is b3, c3, d3, and e3, and so on. Okay. So this is what we will do. So this will multiply the number of experiments, and instead of 10 or 50, it will be 500, because we will repeat each set 10 times, which is a lot of experiments. It's a lot of experiments, and you need to imagine how the experimental work is challenging. Even if we have a very well made setup and everything is fine, the experiments themselves take time, and sometimes things go wrong and you have to repeat experiments, or something will go wrong with the setup and you need to fix it. So it's not like a simple thing that you need to do. And you can imagine that there are cases where the parameters are not only 7, are not only 5, it can be 7 or 8. This case, you have to multiply this by more number of experiments, and sometimes the 10 experiments is not enough. You might need to do 20 or 30 experiments, and then this would be like thousands of experiments now. But now you would say, okay, we will have a lot of people working on this project, and we will do a lot of experiments, and we have time, so we can do this. Now some questions, other questions will appear. The first is, if we are able to do this, let's go back to the this approach here. We said we will change B, C, D, and E. So about this change, are we going to increase them all, decrease them all, increase some and decrease some? We didn't have any idea about the details of this change, and the combined effect of this change. Shall the system behave in a way different than another way if if we increase all of them or decrease all of them, decrease some and increase some? It's something that needs to be studied. So this is a very valid question that will make it even impractical with this approach that we assumed. It's even impractical. There is one other question which is a very important question here. We said in the very beginning, we said that we will keep 4 parameters constant and change one. Let's, for example, say that we want to change the density and keep the viscosity constant. Okay, the only way we can change we can change the density by either changing the fluid that we are dealing with, whether the whole fluid or its composition, dilute it, whatever, or by changing the temperature. These are the two factors, or the two main factors, that will affect the density. But these two factors will also affect the viscosity. Okay, so the assumption that we can change one parameter independently is an impractical assumption. So based on all what we said, we will reach the conclusion that there are a lot of challenges that will make this approach impractical, and we cannot rely on it to get the relation or the effect of these 4 parameters or 5 parameters on X. So the solution to this is to use combined dimensionless parameters. So to combine these into dimensionless parameters, like what we did in the previous example, and using them to do the experiments instead of the original 5 parameters. We will go through this in more details next time. So next time we will try to answer this question: is how can we set or determine these dimensionless parameters? There is an approach that we will discuss, which is called Buckingham Pi theorem, that we can use to get these dimensionless parameters. So this is what we will discuss next time, inshallah. So I'll see you then.